In this lecture, we are going to learn about what we call infinite series. So infinite series. So what is an infinite series? You know that in the previous lecture we learned about sequences. Now we have what we call infinite series. So what's an infinite series? An infinite series is the sum of terms is the sum of an infinite sequence sequence. So infinite series is a sum of an infinite sequence. Now you know that you will see that this question is not obvious. For example, so let's look at the situation. So we have A1, and then we have A2, A3, like that. So that's the sequence. So this is an infinite sequence. Now the corresponding series. So what's the corresponding series? You add the terms. So we have A1 plus A2 plus A3, like that. So this is what we call infinite series. Here, infinite series. So for example, let's look at a situation. So we have A1, an, the nth term is 1. So if the nth term is 1, your corresponding sequence is 1, 1, 1, like that. So you can see that this is gonna converge. Because 1, 1, 1, 1. It doesn't go anywhere, so it's gonna stay at 1. So it's converge. So what is the corresponding series? So let's say S is the series. So you're gonna add the terms. So we have 1 plus 1 plus 1. But you know that it's gonna add it to infinity. So diverge. So you can see that even if you look at a simple problem, you can see that the sequence converge, but when you look at the corresponding series, it's going to diverge. It goes to infinity. So I'm going to give you like several examples just to see how complicated this is. For example, so let's look at these examples. So we have 4 examples. So I'm going to write few. So let's say 1 plus 1/2 plus 1/3 plus 1/4. What do you think? This will be less than 2, less than 3. So actually we can show that this gonna go to infinity. So this total gonna be infinity. It's gonna go indefinitely large. Now I'm gonna make a slight change. I'm gonna change the sign alternatively. So we can have 1 minus 1/2 plus 1/3 minus 1/4, like that. So what I didn't change much. I just changed the sign alternatively. Actually we can show that this is finite and this get log 2. Log 2 is just a number. Okay. So we know that if you have log e, it is 1. E is 2.718. So that means this is less than 2. So that means ln2 has to be even less than 1. So this is even less than 1. So you can see the difference. If you slightly change the number, this is going to be less than 1. How about more examples? How about if you just pick the odd numbers with alternative sign? So 1 minus 1/3 plus 1/5 minus 1/3, and you can see that if you add all those numbers, you're going to end up with pi over 4. How about some even numbers? So let's say we have 1 plus, not all, 1/2 plus 1/4 plus 1/8 plus, if you add them, what do you get? So every time you're going to have the term. So start with 1, and then we have 1/2, 1/8, 1/4, 1/8. Actually you can see that this is exactly 2. So this one is very easy to see why this is 2. So we can discuss that right now, because this is like kind of simple situation. So let's say you get a 1. This is 1. What I'm going to do, I'm going to half it. So this is 1/2. So this is 1/2. Now what I'm going to do, I'm going to half the second piece. So if you half the second piece, you're going to get 1/4. Now I'm going to half the remaining one. You're going to get 1/8. So you can see that you can just continuously do it, but at the end what's going to happen, if you add all of them, you're going to get 1. So this sum is 1. So that 1/2 plus 1/4 plus 1/8, the sum is 1, and when you add 1 extra, so you're going to get the total 2. So let's do one last example. How about this one? Let's say you have 1 plus 1/2 squared plus 1/3 squared plus 1/4 squared. So what you do, you square all of those terms. You square the terms. So when you square and add them, actually you're gonna get pi squared over 6. So in this class, actually we're gonna prove all first 4. We actually prove 1 right now, but we're gonna prove the other ones later. We're gonna prove the first one in this lecture. That one is what we call the harmonic series. We prove that the harmonic series diverge, actually goes to infinity. Other ones we're gonna prove in this course, but not in this this lecture. At the end of this course, we're gonna prove them. When we talk about at the end of this chapter, we're gonna prove. We talk about Maclaurin series and Taylor series, and the last one is like little advanced. Yeah. So you can see that how they behave is like completely different from a regular situation. So we might need to pay little attention, because these things can get weird. Okay, so let's continue. So what we're gonna do is like we're gonna start with the systematic definition, and we're gonna continue the idea about this. So let's start the idea. So we're gonna define what we call partial sum. Partial sum. So what's the partial sum? We're gonna call it Sn. What we're gonna do, we're gonna add the first n terms. That's what we call the partial sum. So we're gonna add the first n terms. So if you add the first n terms, we're gonna call this is the Sn, and we call this a partial sum. Partial sum. Partial sum. The first sum of the first n terms. So we define this, and then we're gonna look at this. So we look at the partial sum. So we're gonna look at S1, S2, S3, and you can see that this can create a sequence. S1, S2, S3, we go like that. So this is Sn, the n term, like that. So this is just a sequence. If this sequence converge, we say the corresponding series converge. So very simple idea. This is completely related to sequences. So if this sequence converge, we say the series converge. So let's look at the definition. So what we have, so if the sequence of partial sums, if the sequence of partial sum, that means Sn, we can write this one as Sn, n going from 1 to infinity, converges, if the sequence of partial sum converges, we say the series converges. So if the partial sum converge, we say the series converge. Okay, so it's just nothing new. We just like introduce a new term. And otherwise the series diverge. Otherwise the series diverges. Otherwise the series diverges. So if the partial sum, the sequence of partial sum does not converge, we say the series diverge. So so if you look at this again, so what we have S1 is simply A1, S2 which is simply A1 plus A2, S3 which is A1 plus A2 plus A3, like that. So we're gonna keep the so you can see that every time you get a number, so that means Sn is, we have A1 plus A2 plus A3, like that, and then we have Sn, so we have sigma k going from 1 to infinity ak. So that's what we have. So this is what we call the actually not infinity, Sn to Sn. So this is what we call the partial sums. You can add up to n, add up to n. This is what we call the partial sum. And there are other notations also, so we can discuss that later. So now what we're gonna do, we're gonna send n to infinity. We're gonna send n to infinity, and that's what we call the sum of the series. So we're gonna send this to infinity. So when you send s to infinity, so so let n goes to infinity. When n goes to infinity, we have s equal s infinity, that is the sum of the series. So a2 a3, like that. So you're gonna get the sum of the series. So we're gonna write it as k going from 1 to infinity a to the k. But sometimes, you know, if it's obvious, sometimes we just write this as sigma ak. So when this is obvious, we don't even write the index. Okay. So so other notations. Other notations. So what are the other notations? So so we basically have three notations. So we're gonna have sigma n going from 1 to infinity an. So remember, whatever the letter you use, just use the same index. Or we can write this one as sigma k going from 1 to infinity a to the k. Or we can just write, if it is obvious, we just write a to the k or a to the n, like that. So those are the notations that we use. When it is really obvious, we don't even write the index. Good. So so what we're gonna do, so you know that the behavior of the series is kind of very chaotic. So what we're trying to do, we're gonna talk about three very important situations in this course. So let's go to the first one, what we call the geometric series. So that's the first one. So the geometric series, and this is very, very important. We're gonna have a lot of applications of this one later. So we have geometric series. So what's a geometric series? So we start with a number, and then every time you multiply by a constant, so a fixed constant. So we use that constant as ar. So we multiply by r. So we start with a and multiply by r. So it becomes ar, and then ar squared, ar cube, like that. So that means if you look at the nth term, it is ar n minus 1, because you start with a. So the nth term is a n minus ar n minus, that's the nth term. So and then this is what we call the geometric series. So this is we call the geometric not the series, geometric sequence. Geometric sequence. And then what we do, we can add the terms. So when you add the terms, so we have a plus ar plus ar squared, like that. So then what we get, what we call the geometric series. So this is the geometric series. Geometric series. So now the question is, how do you know whether when you add these numbers is it finite or not? If it is finite, we say converge. So that means we need to study that. So let's see how we can figure out that. So what we have R here. This R has a name. It's called the ratio. The ratio. It's called the ratio. So and then A is just we call just the initial term. Initial term. That's just the first term. This is what we call the initial term. So what we're going to do, let's look at the partial sum. So we're going to look at the partial sum and then see whether the partial sum as a sequence converge. So the partial sum is A plus AR plus like that. We can have little more terms here just to see what's going on. So I'm going to add like 3 terms here. First 3 terms as A R squared, and then you can write the nth term. So what's the nth term? A R n minus 1. This one I'm going to call equation number 1. Now we can do a simple trick. What we can do, we're going to multiply this whole equation by R. So we're going to multiply by R. So if you multiply this one by R, you're going to get R times Sn AR plus AR squared plus AR cube. That's what happened here. And then the last one become ARN now. Now what we're going to do, we're going to subtract these two. So by we can say 1 minus 2. So if you subtract these two, on this side you're going to get Sn minus RSn. That's what happened on the left side. What will happen on the right side? On the right side you can see that those terms get cancelled. AR get cancelled with AR. AR squared get cancelled with AR squared, and this one get cancelled with the previous term on the other side, and this one also get cancelled with the term left to the bottom one. So that means all of those terms get cancelled because they are equal, but you're subtracting them. So that means you simply end up getting 2 terms. What are the 2 terms you're going to get? The first term of the first sum and the last term of the last one, bottom one. So you get the first term of the first one and the last term of the bottom one, and everything else get cancelled. So that is what you get now. So that means this you can see, this is simply, if you pull out Sn, you're going to get 1 minus R on this side. The other side is become, if you pull out A, you're going to get 1 minus Rn. Now what we can do is we can divide by 1 minus R. We can divide by 1 minus R. So so now if R not equal to 1, if R equal to 1, remember at the beginning we show that it is just 1 1 1 1 is equals to infinity. So we consider here R not equal to 1. So actually let's write that, let's consider that as well. So let's say if R equals to 1, if R equals to 1, your Sn is simply A plus A plus A, like just adding A terms. So and this is A, so there are n many terms. So if there are n many terms, this simply become n times A. But you can see that this goes to infinity, this goes to infinity. If A is positive, this goes to negative infinity if A is negative. So those are the 2 situations that we get. If A is positive, this goes to infinity. If A is negative, this goes to negative infinity. So that means in both cases it's going to diverge. So the situation what we get is diverge. So diverge. Okay, diverge. So now what we're trying to do, so that means that case is gone, because if R equal is going to diverge. So let's say it is not the case. So so if R are not equal to 1, now what we can do is we can divide, we can go back and we can see that if r not equal to 1, then we can divide by that both sides. So we can divide both sides. So you're going to end up getting Sn equal a 1 minus Rn over 1 minus r. So that is what happened if r not equal to 1, and this is a very important result. We can use this a lot in the future. Okay, now let's study two cases. So let's say if the absolute value of r is bigger than 1, if the absolute value of r is bigger than 1, what will happen to Rn? Rn goes to plus or minus 1, because it can fluctuate. You can see if r is positive, then when you increase n, it's going to be like a 2, -3, 4, -5, so it's going to fluctuate. So it's going to if you look at the graph, it's going to happen like this, getting larger and larger. So it's going to fluctuate. That means it's going to diverge in this case. So diverge. So now what if r is, if the absolute value of r is less than 1? If the absolute r is less than 1, what will happen when you increase Rn? R is a number which is smaller, so when you increase, it's getting smaller and smaller. So that means it's going to goes to 0. It's going to goes to 0. So that means in this case, what will happen? The Rn term goes to 0. It's going to goes away. So the geometric series converge. So the geometric series converges. So it's gonna converge if r if absolute r is less than 1, and you can see that there are only two cases. Absolute r less than 1 is going to converge. Absolute r greater than 1 is going to diverge. If r equal to 1, it's also diverge. So what we can do is we can simply include r equal 1 in the condition. So let's write this as a theorem, because this is a very, very powerful result. So we can write the theorem. So the theorem is, if r absolute r less than 1, the geometric series, is equal a plus ar plus ar squared, like that, converges. This converges to what? Because Rn terms goes to 0, so it's converged to S equal a over 1 minus r. That's why it's going to converge. So this can happen when absolute r less than 1. Okay, so this is a very powerful result. So we're gonna remember this result. So this is something you have to remember. So when absolute r less than 1, the series converges to a over 1 minus r. A is the first term, whatever the first term, a, and then divided by 1 minus r. So okay, so and then we can remember a simple result. So you can see that if you draw the corresponding number line, so you can see, so this is 0, and then we have 1 and the -1. So that what it says that if the absolute r less than 1, that means it's between -1 and 1 here. So if it is there, you can see it's going to converge. So in this part, it's going to converge. Outside, it's going to diverge. You can see that this result is slightly different from the integral test. Remember we were talking about the p integrals. In the p integral, what happened? So I'm going to write this here just to kind of remember that. So we had what we call the integral test. p integral, so it's 1 to infinity 1 over x to the p dx. But remember we were talking about this one, if p is greater than, so greater than 1, if p greater than 1, it's going to converge. So it's going to converge. So it's going to converge. And then if p less than or equal to 1, it's going to diverge. So this literally is not exactly same, but it's very close. So if you draw the number line here, now what is the situation here? So this is going to converge if p is more than 1. So it is, so here, so that's where it's going to converge. P integral converge here, and this is 1. So p integral going to converge if it is bigger, and diverge if it is large. And when we're going to use this in the next lecture, when we do integral test. So this is one of the result, but it's good idea to remember this. And here in the geometric series, it's going to converge only between 1 and -1. Outside is going to diverge, but in the p integral, this is what we normally call the p integral. The p integral going to converge if the p is greater than 1. If the p is less than 1, less than or equal to 1, it's gonna diverge. Okay, so this is a very important result, and let's look at like maybe a few examples. So now we have a part of, so we did not finish this yet. And then if, let's try this one, if epsilon r greater than or equal to 1, the series diverges. The series diverges. So this is something that you need to remember. If the r is greater than or equal to 1, the series diverges. So let's try to look at several examples just to see how things are going on. So the first example, so let's say does the following series converge? 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 So if it converges, find the sum of the series. Find the sum of the series. Find the sum of the series. So let's look at the first example. Let's say the series is equal 1 plus 1/2 plus 1/4 plus 1/8 plus like that. And actually we prove that this is going to converge, but let's see what's going on here. So what we're trying to do, we're going to find the r, because we want to check whether this is a geometric series. And how to do that? To do that, what we're going to do, we can divide two consecutive terms. So we can divide these two. So if we divide these two, 1/2 over 1, how much you get? 1/2, and that is the ratio. But we're going to see whether it's there's a common ratio. So we can divide these two. So it is 1/4 over 1/2. You can see it is also 1/2. And divide these two. 1/8 divided by 1/4 is also 1/2, because this is half of the bottom one, so 1/2. You can see that it's common, so that is the r value. So you can see that the r equal 1/2. So that's the first step. We'll find the r. How to do that? Divide two consecutive terms, it's gonna get r. and then you can see that the absolute value of r, which is 1/2, which is less than 1, so that means the series converge. Series converges. Now the sum, we know that the a equal 1, that's the first term, so the sum is s infinity, that's the sum, we write it s infinity, it is a over 1 minus r according to the formula, so let's plug in. So it's a 1 over 1 minus 1/2, that means 1 over 1 over 1/2, but we know that there are two 1/2 in 1, so that means 2, so the answer is 2, so it's going to converge to 2. So we can mark it, we can see that the series gonna converge to 2. It's gonna converge to 2. Okay, so let's look at more examples. B, let's say 2 minus 2/3 plus 2/9 minus 2 over 27, like that. We do the same thing as before, we're going to find the ratio, so we can divide these two, because we want to make sure that it is a geometric series. How to check whether it's a geometric series? We want to figure out that it is of a times ar squared, that type. So to do that we can divide, so it's a negative 2/3 divided by 2, and when you do that you're going to get negative 1/3. Let's also divide these two just to see. So negative 2 over 27 divided by 2 over 9, and you can see the 2 get cancelled, minus sign gets out, and 1 over 27, 1 over 9, so there are 3 of them, so it is like 1, so you're going to get 1/3 again. Okay. So this is like a very simple algebra here, so you're going to get 1/3, negative 1/3 again. This has to be common, okay. That's why we call the common ratio, so it is equal to negative 1/3. Alright, perfect. So that means so it says that r equal negative 1/3, so that means absolute value of r is 1/3, which is less than 1, so the series converge. So the series converges. Okay, you need to write that. Okay, this converge or diverge, so series converges. Now we know, so in this case, so we have a equal 2 in this case, so we can write the sum, so it's infinity, it is a over 1 minus r, so we're going to plug in, so a equal to 1 minus 1/3, because r is negative 1/3, so you're going to get 2 over 1 plus 1/3, and if you multiply the top and bottom by 2, so you're going to get 6 over, if you multiply the top and bottom, you're going to get 3 plus 1, so that means 6 over 4, that means 3 over 2, so 3/2. So that means it's going to converge to 3/2. So that's the total sum you're going to get at the end, so it's converged to 3/2. Let's do maybe one more. C. So how about this one? Let's say sigma n going from 0 to infinity, negative 1 to the n, 5 over Rn. How to do this problem? So you can see that 5 doesn't have n involved, so that means you can pull that out of the series because there's no n in there. So you're gonna get n going from 0 to infinity, negative 1 n, 1 over 4 to the n, right? Oh, you can write this one as sigma, so put 5 out, negative 1 over 4 to the n. So that means it just directly tell you what is the a is, what the r is. So in this case you can see that r is equals to negative 1/4. This says that absolute value r is 1/4, which is less than 1. That means the series converge. series converge because absolute are less than 1. Because we know that if less than 1 converge, greater than or equal to 1 diverge. Now A. What is A? A is the first term. How to get the first term? You have to plug in n equals 0. So it's a 5 negative 1 to the 0 over 4 to the 0. So that means 0 means 1, so you get 5. So A is 5. Now what we can do, we're going to plug in that value to the formula. So it's infinity, which is A over 1 minus R. So it is 5 over 1 minus 1/4. So you can see that this is 5 over 1 plus 1/4. You're going to multiply the top and bottom by 4, so you get 20 over 4 plus 1, so you're going to get 20 over 5. That means 4, so it's going to converge to 4. So if you write those terms and add them, like enough number of terms, you getting closer and closer to 4. Do we ever get 4? Never, because you have to add to infinity. That cannot happen even if you use a computer. So that means you never get number 4, but you're getting closer and closer to 4. Okay, good. So that is the what we call the first type, or what we call the geometric series. So let's go to the second type. So what's the second type? The second type is what we call telescoping series. Telescoping series. So there's like kind of interesting idea. It's called telescoping. So what's gonna happen in this case? You can write your n term an becomes the difference of two consecutive terms. If an is the difference of two consecutive terms. Terms. That means terms next to each other. That's a consecutive means. It's like a A3 minus A2. So you see that? It's a difference between two consecutive terms. Consecutive means the terms are next to each other. For example, so like A5 and A6 are consecutive because they are next to each other. And A6 and A7 are consecutive. Okay, good. So if you can write an as the difference of two consecutive terms, and you can show that there's a nice cancellation going on. So let's look at an example and try to understand the idea. So the first thing, so let's look at example. Test the series sigma going from 1 to infinity, 1 over n plus 1 for convergence. So test the series for convergence. So what you're trying to do, we try to see whether we can write the nth term. So this is nth term. We can write the nth term as the difference of two consecutive terms. You see whether you can write the nth term as a difference of two consecutive terms. And how to do that? To do that, we can use the partial fraction method. So we use partial fractions. Okay, or any basic trick, or basic algebra. Okay, basic, but the partial fraction method is kind of systematic. So how to do it? Remember there are two factors, so we're gonna see whether we can write n plus 1 as a partial fraction. So we can write this as a over n minus b over n plus 1. See, those are the two factors. So and then we try to find a and b. So as before, what we normally do, we're gonna multiply the by the common denominator. So we're gonna multiply by n plus 1, so you get 1 equal a n plus 1 b n. Now what we can do is we can apply n equals 0, then you're going to get a. When you apply n equals -1, then you're going to get b. So actually we can have a minus sign, because you know we kind of force the minus sign because we are waiting for that. But if you do not know, you just start with the plus sign, you know, just start with plus sign, and you can see that b gonna get -1 or something like that. So now what we're gonna do, we're gonna plug in. So when you plug in n equal 0, you apply n equals 0, what will happen? You're gonna get a equal 1. When you plug in n equal -1, when you apply n equal -1, you're gonna get b equal -1. So as expected. So and then you're gonna get a equal 1 and b equal -1. So you're gonna plug in that, and then you can see that because of this, you're gonna get 1 over n plus 1 equal 1 over n minus 1 over n plus 1. This is maybe something you to remember. So you can see that this is a difference of two consecutive terms. So difference of two consecutive terms. Difference of two consecutive terms. So that's exactly what we want. So we kind of win in this situation, because if you cannot write it like that, the telescoping technique does not work. Now let's see what's going to happen. So now we're going to go back. After we do that, we're going to go back to the series and try to write few terms. So we're going to say n. So we're going to look at the nth sum. So in nth sum means what? Is the sigma n going from 1 to actually let's not write n again, because it can confuse you. So we're going to use a different index in this situation just to avoid the confusion. So I'm going to say k. So k goes from 1 to n. Okay, otherwise they are saying n going from n to n. So what is that? So we can write it like that. So that means, and here it's going to be k plus 1. It's the same argument. So because of that, now what's going to happen? Let's write the first few terms. What's the first term? When you apply in k equal 1, your first term becomes 1 times 2. When you apply in k equal 2, your next term becomes 2 times 3, and then 3 times 4, like that. What's the last term you're going to get? Last term you're going to get when you apply n, so you're going to get n plus 1. That's the last term you're going to get in the nth sum. Now what we're going to do, we knew that from the previous partial fraction decomposition, each such product is a difference between two terms. So that means you can write the first term like this. So you can see the first term going to be 1 over 1 minus 1 over 2, because of the sum. Because when we have 1 over n plus 1, it becomes 1 over n minus 1 over n plus 1. Alright, we plug into the formula, and then the next term becomes 1 over 2 minus 1 over 3, and then the next one becomes 1 over 3 minus 1 over 4, like that. So you're going to keep doing that, and what's the last term? It's become 1 over n minus 1 over n plus 1. So that's exactly. Now the magic part. You can see after we write it like that, there's a really nice cancellation going on. It's because of the difference of two consecutive terms. You can see this term get cancels with that term, and then this term get cancels with that term. So just that keep happening, and then this one cancel with the next one, and like that. So this is going to get cancelled out. So you simply end up getting the first term and the last term. Everything else get cancelled out. Now we can actually simplify this one. We can take the common denominator. If you take the common denominator, it is n plus 1 minus 1 over n plus 1. If you simplify this, you simply end up getting n over n plus 1. So that is the partial sum, n over n plus 1. Now what we want to do, we want to send n to infinity to see the infinite sum. So S infinity is simply, we can take the limit. We can take the limit when n goes to infinity of Sn. So that means the limit when n goes to infinity, n over n plus 1. So when it goes to infinity, you know that how we do this kind of things, we can ignore the 1 here because n goes to infinity. So that means it's simply going to be the limit of n over n, because you can ignore 1 in this kind. You only need to consider the largest term of the numerator and the denominator. We only need to consider the largest term of the numerator and the denominator. You can see that get cancelled, so you simply end up getting 1. But you can also use the calculus 1 technique. You can divide the top and bottom by n, but we don't want to do that anymore. That's in calc 1. Now we only need to consider the largest term of the numerator and the denominator. Good. So you can see that now it simply converges to 1. So that means converges to 1. So that is the infinite sum of the series. So if you add such terms infinitely, you simply end up getting 1. So please remember this technique. So this is what we call the telescoping series. So this is a very common trick we use, and it's a very, very important technique. So this is what we call the telescoping series. Telescoping means cancelling like that is called the telescoping. So this is called the telescoping. So I'm going to write it here. So this cancellation is called the telescoping. Okay, so it's gonna cancel it like that. It's called the telescoping. They cancel each other and only get the first and the last. So that's exactly what happened in a telescope. So when you have a lot of lenses, so what worry about is the first one, the last one. So you can see other things changes, but at the end, what is important is the first and the last. That's how you call it telescoping here. Okay, so I'm going to give you a few more examples for you to try. So so what about this? So I'm going to say, so this is for you to try. Test whether the following series converge. Okay, so the first one, let's say sigma n going from 1 to infinity 3 over 2n minus 1 and then 2n plus 1. So do the same thing, just try to write the partial fraction decomposition, and so it's a very simple calculation. It's exactly like that. How about this sigma n going from 1 to infinity, so we have 5 over sine inverse 1 over n minus 5 over sine inverse 1 over n plus 1. Okay, you can see there's already a difference, so you don't have to do much here. So just a simple calculation, because you can see that the nth term is already a difference of 2 consecutive terms. It's n plus 1, n plus 1, so 2 consecutive terms. So so that's an, but this is already a difference between 2 terms. Okay. So this looks like we can say b n plus 1 minus bn. It looks like that. So it's a difference between 2 terms. Okay, so you can just follow the same technique that we discussed to do these problems. These are very simple, you can see, but why don't you try this? Okay, good. Now let's try to look at what we call the nth term test for divergence. So that's a very important test. So what we try to do now, so now we test like 2 types. We still have one more type. So what we try to do, we're going to test whether a series, how to test whether a series like diverge. The converge part, we know like few things. We talk about the geometric series already, how to check that when the absolute r less than 1 is going to converge. And then we had this telescoping series, but you need to kind of look at the partial sum, and then you trade the limit, and if the limit going to converge to a number, and you can see that it's going to converge. So if you get a number, it's going to converge. So we only know 2. So then there's a very important result. That's what we call the test nth term test for divergence. Okay, so simply call the test for divergence. So nth term test for nth term test for this only for divergence, unfortunately. Divergence. So we cannot test converge from this test. Okay, only works for divergence. Only works for divergence. So so let's see how things going on. So let's look at like one example just to kind of get the idea. So consider the series. Consider the series sigma n going from 1 to infinity n plus 1 over n. So let's look at this series. So that means this is simply sigma n going from 1 to infinity a n, right? A n. So where a n equal n plus 1 over n, or this is simply the nth term. So this is the nth term. This is the nth term. So now what we do, let's take the limit of this one. So we take the limit. So let's take the limit. So the limit when n goes to infinity, a n is the limit n goes to infinity n plus 1 over n. So and you can see that if you consider only the largest term from the top and bottom, it is n of n, which is 1. So you're going to get 1 here. So what does that mean? That means when n gets larger, the terms looks like 1. That's what it means. When n gets larger, the terms looks like 1. Okay, so this means that this idea is very important for the future. Okay, this means that when n is large, an is almost, when an is almost looks like an is almost looks like 1. Almost looks like 1. So it's not 1 but very close to 1, looks like 1. So that means what we are doing, we are simply adding 1 1 1 1 1. That's what happened. So you are simply adding that same number. It looks like. So that means it's going to go to infinity because you are adding a same number infinitely many times. Okay, so that means we are adding, because it's a series, it's a sum, we are adding terms such as 1. So it's a very important idea. We are adding terms such as 1. So what will happen? 1 indefinitely. So you are adding the term indefinitely again and again and again. So that means the series diverges to infinity. So the series diverges to infinity. So it's a diverge to infinity situation. Diverge to infinity. So what infinity? It depends, because here it looks like 1. It's a positive number. So that means if the limit is positive, it goes to positive infinity. Similarly, you can get like -2 when you do that, or -1/2. So those are negative numbers. So if the negative number, that means goes to negative infinity. So depending on the limit, it becomes either positive infinity or negative infinity. Okay, so we just need to check the limit. So So simply we can say if the limit n goes to infinity an is positive, then it's gonna go to s infinity goes to positive infinity. If it is negative, any number, just a negative number, negative, then Sn goes to negative infinity. So depending on what sign you get, if you get a positive number, it goes to positive infinity. If you get a negative number, it goes to negative infinity. Very good. So let's try the theorem now, the result. So what's the result? So theorem. So there are two results actually. So I'm going to write those two results. So the first one, if a series converge, if a series converge, an converges. Now it's a, if the series converges, then an goes to 0. The nth term has to be 0, should go to 0. So this is very important. Okay, so this is this is very important. This is very important. This is very important. How to prove this? Let's prove this result. So what we can do, so let's look at the proof, how this works. So let S equal the sum. So you're going to say the sum of the infinite series. Then what is an? Then an is the sum up to n many terms minus sum up to n minus 1 terms. So that an means you sum up to n minus sum up to n minus 1. Okay. Now what happened? We know that series converge. Since the series converge, so as n goes to infinity, an, which is Sn minus Sn minus 1, goes to what? Sn goes to S, that's the full sum of the series, minus Sn minus 1 also goes to S, because it just doesn't matter whether you have n or n minus 1, n goes to infinity. So that means, but they are equal, so you get 0. So you can see that. So that means an simply become 0. Okay, so an has to be, so that means if the series converge, you can show that an, the limit of as n goes to infinity. Okay, it's not any other time. So if as n goes to infinity, Sn, actually we should not write equal sign here. It's not equal, it says goes to, so it's an arrow. So reach S minus S, that means 0. Okay, so that's the result. That means if a series converge, the nth term goes to 0. So that's not the case. So what does that mean? So if the series converge, the nth term goes to 0. So that means if the nth term is not equal to 0, the series cannot converge. Because we know that if the series converge, nth term has to be 0. So if you know that beforehand, if the nth term is not equal to 0, there's no way that the series can converge, because we know that if the series converge, it has to be 0. So let's write, so I'm going to write this as a knot. So the knot is the converse. Okay, converse is the opposite one. Converse of this theorem, converse of this theorem is very important. Okay, very important. To prove that a series is divergent. Okay, but unfortunately it doesn't work for convergent. It's only say for divergent, because it doesn't say that, you know, if this happened, series converge. It doesn't say that. It only says that if the series converge, n has to be 0. That's the only thing it says that. So we can test, but if we know that if n does not go to 0, then the series cannot converge, because if it converge, it has to be 0. Okay, so that's why the converse is important. So let's try this in detail. So I'm going to write this in words. The theorem says that the theorem says that if a series converges, an has to go to 0. Okay, the limit of an has to be 0. The limit as n goes to infinity. So if we know that, the limit of an not equal to 0, okay, something else, not 0. So how can that happen? That means what? That means the limit, there are two things. That means the limit does not exist, or limit is something else. Okay, it is L but which is not equal to 0. You get something else. That's it. Okay, so L not equal to 0. Then the series cannot converge. Okay, it's a really nice argument. Cannot converge. Series cannot converge. Very good. Because I'm going to write more. Because if the series converges, the limit has to be 0. The limit of n has to be 0. Okay, so if it is not equal to 0, that means the first thing cannot happen, otherwise it can contradict. Okay, good. So let's try the theorem now. So this is what we call the nth term test. So let's try it. So the theorem, the nth term test, nth term test for a divergence. Nth term test for divergence. Nth term test for divergence. So we look at the nth term. Okay, so what is that? So look at the series. So in going from 1 to infinity, an diverges if the limit n goes to infinity, an not equal to 0 or does not exist. Okay, so you simply check the limit. If the limit not equal to 0, so if the limit so it diverges if the limit not equal to 0 or does not exist. Okay, that's what we call the nth term test for divergence. Nth term test for divergence. So but in a problem what we need to do is, so you only need to check the limit of the nth term. You only need to check the limit. You only need to check the limit of the nth term. So we just take the limit, that's it, and that tells you whether it diverges or not. Okay, but it doesn't say anything about the convergence. Okay, so does not say, I'm going to write it again, does not say anything. Does not say anything about convergence. Okay, does not say anything about convergence. Okay, so let's try to do some examples to see how we can use this idea. So the example, so test the following series, for convergence. The first one, sigma n going from 1 to infinity n squared. So what will happen when n goes to infinity? This goes to infinity, so the series has to diverge. Okay, diverges since n squared goes to infinity, and which is not 0. It's very clear. B, how about this one? So we can do like several different examples. N over n plus 1 diverges since n over n plus 1, what about this limit? N over n plus 1 goes to, because you only look at the n, and n is 1, so it goes to 1, which is not equal to 0. Okay, how about this? C, sigma n going from 1 to infinity negative 1 n diverges since the limit n goes to infinity negative 1 n, that's the nth term, does not exist. We don't know the limit, it's just fluctuate between 1 and negative 1. Where is ends, we don't know. So this is like oscillating. Okay, oscillating means does not converge. So oscillating, when oscillate, this doesn't converge. How about this one? So the sigma n going from 1 to infinity 2 n squared minus 3 over we can say 5n minus 4n squared. 2n squared minus 3 over 5n minus 4n squared. So you can see this also diverges. Why? Diverges since the limit, what's the limit of this one? 2n squared minus 3 5n 4n squared. If you consider only the largest term from the numerator and denominator, you get 2n squared over 4n squared. That means you're going to get negative 2 over 4, which is negative 1/2, which is not equal to 0. So diverge, because it's not 0. It's not 0. So you can see it's negative 1/2. So the series diverge. Okay. So what about the last example? How about this one? Yeah, you can see there are a lot of things to discuss. So how about sigma n going from 1 to infinity 1 over n? What will happen if converge or diverge? 1 over n goes to, so note that 1 over n goes to 0, right? But the question is, can we say anything? Can we say anything about the convergence? Can we say anything about the convergence? But we know that when it goes to 0, we don't know. When it not go to 0, we can say something, but if it goes to 0, we can say anything about this. So so let's write it again. Something that we just write. Test for divergence. It's only for divergence. You can see test for divergence. Test for divergence does not say anything. Does not say anything about convergence. Okay, it's only for divergence. It's only for divergence. Good. Actually, we can show that. We can show that the sigma 1 over n diverges. Even if 1 over n goes to 0. Even if 1 over goes 0. Okay, so let's do that. Okay, so let's do that. So that's the third example, third type. So this is what we call the harmonic series. So the example, it's a third example. It's a very, very important example. We use this a lot in the future. Harmonic series. Harmonic series. It's called the harmonic series. Sigma 1 over n called the harmonic series. So harmonic series diverges. And how we do that? So this is the kind of argument. So let's look at a like few terms. Okay, so see sigma n going from 1 to infinity 1 over n. So I'm going to write first few terms. 1 plus 1/2 plus 1/3 plus 1/4 plus, and then we have 1/5 plus 1/6 plus 1/7 plus 1/8, like that. So what we're going to do, we're going to group them in a kind of interesting way. So how we group them? We're going to group 1/2 just one term, and then we're going to group 2 terms, and then we're going to group 4 terms, and then we're going to group 8 terms, like that. Now what's going to happen? Let's look at the argument. So you can see that if you consider the smallest one in each group, the sum is larger. So if I do, you can say this is greater than 1 plus 1/2. You don't see anything here, but what we can do, I'm going to replace in this group, I'm going to replace the rest of the term by the smallest. What is the smallest here? 1 over 4. So I'm going to put 1 over 4 here. So you can see that this sum is smaller than the sum above it. Plus here we're going to replace the group by the smallest one. So 1 over 8, 1 over 8, 1 over 8, 1 over 8. So in the next one you can see is a 1 over 16, like that, and then 1 over 32, like that. So we replace each term within the group by the smallest one. Now you can see this can add it up. So you're going to get 1 and then 1/2. If you add 1/4, 1/4, it's about 2/4. That means it is a 1/2. If you add, so actually I can write it a little bit more. I can write one more step. So what's going to happen here is you're going to get 2/4. Then you're going to get 4/8, like that, and then you're going to get, if you continue this, you're going to get 8. You're going to get 8/16. Okay, so you're going to get 8/16. So just like that. But you can see, what are these? This is simply 1, 1/2, 1/2, and then again another 1/2, and again another 1/2. So what you are doing, we are simply adding terms, 1/2, 1/2, 1/2, 1/2. So the sum goes to infinity, because you're going to add 1/2 indefinitely. So that means sum goes to infinity. It can be larger than any number you like. Okay, so yeah, but so you can see the sum is, so that means, so this sum is going to infinity, but this is smaller than the original sum. So that means the original sum also has to goes to infinity, because this is smaller one, which is goes to 0 infinity. So that means the original one has to go to infinity. But you can still see that even though this is the case, but you can see that an, which is 1 over n, goes to 0 as n goes to infinity. Even though the term goes to 0, but you can still see that when you add enough terms, the sum can be larger than any number you like. Okay, so now let's finish the argument. So you can see that since the right hand side RHS, right hand side goes to infinity, the left hand side LHS of that argument also goes to infinity as n goes to infinity. Okay, when you have large and larger terms, you can see the right hand side goes to infinity, so the left hand side has to go to infinity as well. So for example, so now what is numbers? This converge very, very slowly. So for example, if you want to find how many terms you need to get to, let's say, yeah, you're looking for how many terms you need. So let's say you need you're adding m many terms. So the question is how many terms you need to add of this series to get to just bigger than 20. And you can see that you need so you need, how much you guess? How many terms you need? You need about 178 million terms. So you can see that this converge very slowly, very slowly. So just to go about 20, you need about 178 million terms. So it's not very it's not like very fast convergence. So the next question will be how many more terms you need to pass 21. So the question is how many more terms needed to pass 21. Okay, so try to do that, and this considers an extra credit problem, and you can email me. So see how many more terms you need just to pass 21. So I'm asking, you start with 20, so you need 178 terms, but how many more terms you need to pass 21? So that's a kind of interesting question, but you need a computer, so you need some kind of programming skills to do this. Okay, so but that's a good challenging problem. Okay, so yeah, so those are the three types. So now what we're gonna do is we're gonna see how to add you know what we can do next. So we can combine those series. So let's talk about that, and that's the last thing we're gonna do here. Combining series. So combining series. So what we do, combining means you can add, subtract, and then constant multiply. Okay, so the theorem is if sigma an equal a and sigma bn equal b, so that's a sum, are convergent, Okay, a convergent series. Let's say you have two convergent series. An converges to a simple an converges to a, and bn converges to b. So then what happen? Then we can do all these interesting things. So the sum. So you can sum it. So the an plus bn. You can see that an plus bn create a new sequence, which like cn. You can just call it cn. So now the question, when you add them, what's going to happen? So it is sigma an. So what it says that you can split this. This is this. But it's, remember, it's if these series converge. So if it doesn't converge, you can do this. Okay, so you can split it. So that means your sum going to be a plus b. But it's only if they converge. It doesn't converge, you can do this. And the difference. So it's very similar. So if you have an minus bn, so you can do the same thing. You can split it. So it is an minus bn. So it is a minus b, and then you can constant multiply. Constant multiply. So if you have a constant like a k times an, you can just pull the k out. So sigma a. So in this case ka certificate. Now the question is, if you multiply two series, that's actually complicated. Okay, when you multiply two series, that's going to be complicated. So we don't do that. So in this class, so this is complicated. So you're going to multiply two. Okay, complicated. So, but we can see what are the first few terms. You know, just take the first few terms of the first few terms of the second one, and multiply. That you can do. But if you want to write a formula, that's going to be complicated. Okay, good. So let's have like a small note. So how about this? So so I'm going to have few things. Every non-zero constant, every non-zero constant multiple, every non-zero constant multiple, every non-zero constant multiple of a divergent series. Divergent series is divergent. Okay, every constant multiple of a divergent series is divergent. That's the first one. And then we have, if a series n converges, if a series converges and sigma bn diverges, so one converge, one diverge. Okay, one converges and one diverges, then the sum, what do you think? Then the sum, but the convergence has a finite number. So, but what will happen to the other one? So other one goes to infinity, so everything goes to infinity. So, and the sigma n minus bn, they both diverge. Both diverges. Okay. So if you have a one converge, one diverge, then if you look at the sum, it's diverge. When you look at the minus difference, they still diverge. Okay. So if you just add a convergent series, it doesn't change the behavior of the original series. So that's what it means. And then so what about this one? If sigma an and sigma bn are both diverges, what can you say about the sum or difference? Actually, it can be anything. We cannot say anything about the convergence. We cannot say anything about the we cannot say anything about the a plus or minus b. We cannot say anything. So anything can happen. Okay, so think about examples. Think about a situation where you have both diverge and the sum converge, and think about a situation where both diverge but the difference diverge. Okay, so think about examples. Yeah, think about examples where one converge and one diverge. So that's interesting example. Okay, so let's do just few things. Actually, I would like to give you one such example. For example, let's see this example. So let's say sigma an equal 1 plus 1 plus 1, like that. So you know that this diverges to infinity, diverges to positive infinity. How about sigma bn, which is negative 1, negative 1 plus negative 1 plus negative 1, like that. I just put the parentheses just to exaggerate. So this also diverges to negative infinity. What about the sum n plus bn? So you can see that it is simply 0. So 0 plus 0 plus 0, that's just 0. So converges. So you can see that. So there's annihilation between the two, so that goes away. Okay, good. So but now what this says, this is algebra. So what this theorem says, that if we know those series converge, then you can add them and subtract them and multiply by constant. So that's very useful. This is a very useful result. It says that you can split it. Your series, you can split them. So let's see how we can apply them into problems. Okay, so example, so find the sum of the following series. Find the sum of the following series. The first one, sigma n going from 1 to infinity, 3 n minus 1 over minus 1 over 6 n minus 1. So n going from 1 to infinity, 3 n minus 1 over 6 n minus 1. So what we can do, we can split this using the theorem that we just had. We can write this in a two series. So we have 3 n minus 1, 6 n minus 1 minus sigma n going from 1 to infinity, 1 over 6 n minus 1. And then we can combine, and we can write this as geometric series. What we can do, we can combine them. So you can write this one as, we combine 3 and 6, so it become 1/2 to n minus 1 minus, and sigma n going from 1 to infinity, you can rewrite this one as 1 over 6 n minus 1. And you can see that these are geometric series, because when you use r to the n, it's a geometric series. So these are two geometric series. That means we can use the result from the geometric series. We know the sum formula, so we're going to use the sum formula. So we can see that in this case r is 1/2, in this case r is 1/6. Okay, so if you use the sum formula, you can see that this is 1 over, that's the first term. To get the first term, plug in n equal 1. When you plug in n equal 1, you're going to get 1/2 to the 0, that means 1. So 1 over 1 minus r, that means 1/2, minus, here the first term, same, when you apply n equal 1, you're going to get 1 over 6 to the 0, that means 1. So it's 1 over 1 minus 6. So you can simplify these two. So where this is coming from? So this is coming from, we know that the S infinity is a over 1 minus r. Good. So you can simplify. So you're going to get 1/2, and then 1 over 1/2, that means 2, minus, here you're going to get 1 over 5/6, so the 6 over 5. and then if you simplify, you can multiply 10 minus 10 minus 6, that means 4, so it's a 4/5. You can see it's finite, so converges. Okay. And also actually you know that it's converged because R is 1/2, so those both series converge there. So you can actually write it, so you can say the absolute value of this less than 1, so the absolute value of this is less than 1, so both converge. Okay, they both converge. Good. So let's look at another example. So you can see it's very simple. How about this one, B? So sigma n going from 0 to infinity, 4/2 to the n. So this is very similar. You take the constant out, so it's n going from 0 to infinity, 1/2 to the n. In this case, r equal 1/2. So this says that the absolute value is 1/2, which is less than 1, implies converges. So so it converges to a over 1 minus r. So the a means when you apply n equals 0, you get 1/2 to the 0, that's a, so it's 1 over 1 minus r. R is 2, 1 over 2, 1/2, so it's you're gonna get 2 times 2, so that means 8. So this one converts to 8. So you can see that these are like kind of interesting examples. So this is very useful. Yeah, so this is how you kind of do examples. So this is the end of the series, introduction to series. And then what's gonna do in the next lecture, we're gonna kind of consider several different tests. So there are several different tests that we need to know. We're gonna call integral test, comparison test, direct comparison, limit comparison, and the ratio test, root test, integral test, alternate series test. So there are 6 tests. So we're gonna talk about that in the coming lectures. Thank you.